most topics, you have to get pretty advanced before you start addressing the philosophically interesting things. But in chemistry, it just starts right from the get-go with what's arguably the most philosophically interesting part of the whole topic, and that's the atom. And the idea of an atom is philosophers long ago, and you could look it up on the different philosophers who first philosophized about it. They said, hey, if I started off with, if I started off with an apple, and I just kept cutting the apple. Let me draw a nice looking apple just so it doesn't look just like a heart. Or there you go. Have a nice looking apple. And you just kept cutting it, smaller and smaller pieces. So eventually you get a piece so small, so tiny, that you can't cut it anymore. And I'm sure some of these philosophers went out there with a knife and tried to do it, and they just felt that, oh, if I could just get my knife a little bit sharper, I could cut it again and again. So it was a completely philosophical construct, which frankly in a lot of ways isn't too different to how the atom is today. It's really just a mental abstraction that allows us to describe a lot of observations we see in the universe. But anyway, these philosophers said, well, at some point we think that there's going to be some little part of an apple that they won't be able to divide anymore, and they call that an atom. It doesn't have to just be for an apple. They said this is true for any substance or any element that you encounter in the universe. And so the word atom is really Greek for uncuttable. Uncuttable or indivisible. Uncuttable. Now we know that it actually is cuttable, and even though it is not a trivial thing, it's not the smallest form of matter we know. We now know that an atom is made up of other more fundamental particles. And let me write them. So we have the neutron, and I'll draw in a second of how they all fit together in kind of the structure of an atom. We have a neutron, we do have a proton, and we have electrons. Electrons. And you might already be familiar with this. If you look at the old videos about atomic projects, you'll see a drawing that looks something like this. Let me see if I can draw one. So you'll have, something like that, and you'll have these things spinning around that look like this. They have orbits that look like that, and maybe something that looks like that. And the general notion behind these kind of nuclear drawings, and I'm sure that they still show up at some government defense labs or something like that, is that you have a nucleus at the center of an atom. You have a nucleus at the center of an atom. And we know that a nucleus has neutrons and protons. Neutrons and protons. And we'll talk a little bit more about which elements have how many neutrons and how many protons. And then orbiting, and I'm going to use the word orbit right now, although we'll learn in about 2 minutes that the word orbit is actually the incorrect, or even the mentally incorrect way of visualizing what an electron is doing. But the old idea was that you have these electrons that are orbiting around the nucleus, very similar to the way the Earth orbits around the Sun, or the Moon orbits around the Earth. And it's been shown that that's actually a very wrong way, and there's a lot of and when we cover quantum mechanics, we'll learn why this doesn't work. What are kind of the contradictions that emerge when you try to model an electron like a planet going around the sun. But this was kind of the original idea, and frankly I think this is kind of the idea that is the most mainstream way of viewing an atom. Now, I said an atom is philosophically interesting. Why is it philosophically interesting? Because what we now view as the accepted way of viewing an atom really starts to blur the line between kind of our physical reality and everything in the world is just information. There really isn't any such thing as true matter or true particles as the way we define them in our everyday life. For me, a particle, it's like a grain of sand. I can pick it up, touch it, while a wave, that could be like a sound wave. It could be this change in energy over time. But we'll learn, especially when we do quantum mechanics, that it all gets jumbled up as we start approaching the scales or the size of an atom. But anyway, I said this was an incorrect way of doing it. What's the correct way? So it turns out, let's see, this is a picture not a picture really. This is also a depiction. So it's an interesting question what I just said. How can you have a picture of an atom? Because it actually turns out that most wavelengths of light that especially the visible wavelengths of light, are much larger than the size of an atom. So it's not like something you can even, everything else we quote unquote observe in life, it's by reflected light. But all of a sudden, when you're dealing with an atom, reflected light is almost, you can almost view it as too big or too blunt of an instrument with which to observe an atom. Anyway, this is a depiction of a helium atom. A helium atom. A helium atom has 2 protons and 2 neutrons, or at least this helium atom has 2 protons and 2 neutrons. And the way they depict it here in the nucleus, right there, maybe these are the 2. I'm assuming they're using red for proton and purple for neutron. Purple seems like more of a neutral color, and they're sitting at the center of this atom. And then this whole haze around there, those are the 2 electrons that helium has, or that at least this helium atom has. Maybe it could, gain or lose an electron. But these are the 2 electrons. You say, hey Sal, that doesn't make, how can 2 electrons be this blur that's kind of smeared around this atom? And that's where it gets philosophically interesting. So you cannot describe an electron's path around a nucleus with the kind of traditional orbit idea that we've encountered when we look at planets, or if we just imagine things at kind of a larger scale. It turns out that an electron, you cannot know exactly its momentum and location at any given point in time. All you can know is a probability distribution on where it is likely to be. And the way they depicted this, black is a higher probability. So you're much more likely to find the electron here than you are here. But the electron really could be anywhere. It could even be here, even though it's completely white there, but with some very, 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 very low probability. And so this function of where an electron is, this is called an orbital. Orbital, not to be confused with orbit. Orbital. Orbital. Remember, an orbit was something like this. It's like the Venus going around the sun. So it's very physically easy for us to imagine. While an orbital is actually a mathematical probability function that tells us where we're likely to find an electron. And we'll deal with a lot more of that when we cover quantum mechanics, but that's not going to be in the scope of this kind of introductory set of chemistry lectures. But it's interesting, right? An electron its behavior is so bizarre at that scale that you can't, to call it a particle is almost misleading. It is called a particle, but it's not a particle in the sense that we're used to in our everyday life. It's this thing that you can't even say exactly where it is. It can be anywhere in this haze, and we'll learn later that there are different shapes of the hazes as we add more and more electrons to an atom. But that, to me, that's, it starts to address kind of philosophical issues of what matter even is, or, do the things we look at, how real are they, or how real are they at least as we've defined reality. Anyway, I don't want to get too philosophical on you. But the whole notion of electrons, protons, they're all kind of predicated on this notion of charge. And we've talked about it before when we learned about Coulomb's law, and you could review Coulomb's law's videos in the physics playlist. But the idea is that an electron has a negative charge. A proton, sometimes written like that, has a positive charge, and a neutron has no charge. And so that's what was tempting about the original model of an electron, is that they say, okay, if this thing has positive charges, right? Because let's say this is 2 neutrons and 2 protons. Let's say it's the helium atom. Then we'll have some positive charges here. We have some negative charges out here. Opposite charges attract. And so, if these things had some I guess you could call some velocity, they would enough velocity, they would orbit around this. It's just the way a planet will orbit around the sun. But now we learn, even though this is kind of partially true, that the further away an electron is from the nucleus, it does have more, I guess you could, it's true, potential energy, in that it will want to move towards the nucleus, but because of all of these, the mechanics at the quantum level, it won't just do something simple like move in a path like that, like a comet would do around the sun. It actually has this kind of wave-like behavior where it just has this probability function that describes it. But the kind of the further away an orbital, it does have more potential, and we're going to go a lot more into that in future videos. But anyway, how do you recognize what an element is? I've talked a lot about the philosophy and all of that, but how do I know that this is helium? Is it by the number of neutrons it has? Is it by the number of protons it has? Is it by the number of electrons? Well, the answer is it's by the number of protons. So if you know the number of protons in an element, you know what that element is. And the number of protons, this is defined as the atomic number. Atomic number. Now, so how do you, let's say I said something has 4 protons. 4 protons. How do we know what it is? Well, we could, if we haven't memorized it, we could look it up on the periodic table of elements, which we'll be dealing with a lot in this playlist. And you'd say, oh, 4 protons, that is beryllium. Right there. And the atomic number is the number that you see up there, and that's literally the number of protons. And that is the single most that is what differentiates one atom from another. If you have 15 protons, you're dealing with phosphorus. Now all of a sudden, if you have 7, let's say you have 7 protons, you're dealing with nitrogen. If you have 8, you're dealing with oxygen. That is what defines the element. Now we'll talk in the future about what happens with charge and all of that, or what happens when you gain or lose electrons. But that does not change what element you're dealing with. And likewise, when you when you change the number of neutrons, that also does not change the element you're dealing with. But that leads to an obvious question of, well, how many neutrons and electrons do you have? Well, if a atom is atomically neutral, is charge neutral, that means it has the same number of electrons. And so let's say that I have a carbon. Let's say let's say carbon. Its atomic number is 6, and let's say its mass number is 12. Now, what does this mean? So let me say further that this is a neutral particle. This is a neutral atom. So the atomic number for carbon is 6. That tells us exactly how many protons it has. So if I were to draw a little model here, and this is in no way an accurate model, I would draw 6, 2, 3, 4, 5, 6 protons in the center. Now, and the weight of these protons, each proton is 1 atomic mass unit, and we'll talk more about that, how that relates to kilograms. It's a very small fraction of kilogram, roughly I think it's like 1.6 times 10 to the minus 27th of a kilogram. So let's say each of these, let me write that, each of these are 1 atomic mass unit, and that's approximately equal to, I think, 1.67 times 10 to the minus 27 kilograms. This is a very small number. It's actually it's almost impossible to visualize, at least it is for me. This tells me the mass of the entire carbon atom, this particular carbon atom, and this can actually change from carbon atom to carbon atom. And this is essentially the mass of all of the protons plus all of the neutrons. And each proton has an atomic mass of 1 in atomic mass units. And each neutron has an atomic mass of 1 atomic mass unit. So this is really the number of protons plus the number of neutrons. So in this case, we have 6 protons, so we must also have 6 neutrons. 6 neutrons plus 6 protons. Now, where are the electrons? Well, I said it's neutral. So the proton has an equal positive charge as the electron's negative charge. So this is a neutral atom, and it has 6 protons, so it also has 6 electrons. So let me draw that. So we said it has 6 neutrons in here. 1, 2, 3, 4, 5, 6. So that's the nucleus right there. And then if we were to draw the electrons, well, I could draw it as a smear, but if we want to kind of visualize a little better, we could say, okay, there's going to be 6 electrons orbiting here. 1, 2, 3, 4, 5, 6. And they're going to be moving around in this unpredictable way that we would have to describe with a probability function. And so, and the interesting thing about it is most of the mass of an atom is sitting right in here. I mean, you might notice that when people care about the mass when they care about kind of the atomic mass number of an atom, they ignore the electrons, and that's because the mass of a proton, one proton, mass-wise, is equal to 1,836 electrons. So for thinking about the mass of an atom, for all for all basic purposes, you can ignore the mass of an electron. That it's really the mass of the nucleus that counts as the kind of mass of the atom. Now you might see this periodic table here, and you say, okay, they gave us the atomic number up there, right? The atomic number of oxygen is 8. It means it has 8 protons. The atomic number of silicon is 14. It has 14 protons. Now what is this right here? Let's see in carbon. Carbon, they have this 12.0107. That is the atomic weight of carbon. So let me write this right there. Atomic weight of carbon. And the atomic weight of carbon is 12.0107. Now what does that mean? Does that mean that, carbon has 6 protons? 6 protons, and then the remaining 6.0107 neutrons, it has kind of this fraction of a neutron? No, it means if you were to average all of the carbon, all of the different carbon versions of carbon you find on the planet, and you were to average the number of neutrons based on the different on the kind of the quantity of the different types of carbon, this is the average you would get. So it turns out that carbon, the two major forms, the main one you'll find is carbon 12. So that's like this. So that has 6 protons and 6 neutrons. And then another isotope of carbon. Now an isotope is the same element with a different number of neutrons. Another isotope of carbon is carbon 14, which is much more scarce on the planet. We don't know how much, in the universe, but on the planet. Now if you were to average these, not just a straight up average, then you would get, carbon 13, and then the atomic weight would be 13. But you weight this one much higher because this exists in much larger quantities on Earth. I mean, this is pretty much all of the carbon that you see, but there's a little bit of this. So if you weight them appropriately, the average becomes this. So most of the carbon you'll find, so if you just found carbon in some place, on average, its weight in atomic mass units is going to be 12.0107. But that idea of an isotope is an interesting one. Remember, when you change the neutrons, you're not changing the actual fundamental element. You're just getting a different isotope, a different version of the element. So these two versions of carbon are both isotopes. Now, I want to leave this video, which I think is kind of the neatest idea behind atoms, and it's kind of the most philosophically interesting things about them, is that the relative size. So we have this electrons, which represent very little of the mass of an atom. I mean, it's 1/2000th of the mass of an atom are in the electrons, and even them, it's hard to even describe them as particles because you can't even tell me exactly where and how fast one of these particles is moving. They just have a probability function. So most of the atom is sitting there inside the nucleus, and this is the interesting thing. If you look at an atom on average, if you say, this is my atom, and let's say I had 2 atoms that are bonded to each other, and I would say, how much of this is actual stuff? And when I say stuff, that's a very abstract concept because we're talking about the nucleus, right? Because the nucleus is where all the mass is, all the stuff. It turns out that it's actually an infinitesimally small fraction of the volume of the atom, where the volume of the atom, it's hard to define because the electron can pretty much be anywhere. But if you view the volume as where you're most likely to find the electron, or with 90% probability you're likely to find the electron, then the nucleus is, in a lot of cases, and the way I think is, but 1/10,000th of the volume. So if you think about it, when you look at something, if you look at your hand, or if you look at the wall, or if you look at your computer, 99.999% of it is free space. It's nothing. It's vacuum. It's if you were to just if you had ultra small I guess we could call them particles or something, most of them would pass straight through whatever you look at. So it already starts to kind of question our holds on reality. What is there when, if, and this is fact, this isn't theory right here, that if you take anything down to the building blocks, down to the atomic level, most of the space of that kind of quote-unquote object is free vacuum space. You could go straight through it if you could get down to that scale. I mean, this is this image of a helium atom. They say right here, this is 1 femtometer, right? 1 femtometer. 1 femtometer. This is the scale of the nucleus of a helium atom, right? 1 femtometer. This is 1 angstrom, right? And they say that equals 100,000 femtometers. And just to get a sense of scale, 1 angstrom is 1 times 10 to the negative 10 meters, right? So the atom is roughly on the scale of an angstrom. In the case of helium, the nucleus is even a smaller fraction. It's 100,000th. So if you had, let's say you had liquid helium, which you'd have to get very cold to get. If you're looking at that, most of it is free space. If you're looking at an iron bar, the great majority of it is free space. And we're not even talking about what's, maybe there's some free space inside the nucleus that we could talk about in the future. But to me, that just blows my mind that most things we look at are not really solid. They're really just empty space, but they look solid because of the way light reflects on them or the forces that repel us. But there really isn't kind of something to touch there. That most of this right here is all free space. I think I've said the word free space now, and I think I'll leave further mind-blowing to the next video.